Welcome. I'm Bill Wake. We're here working on a program to compare tunes for similarity. Lately, we've been working on clustering, so trying to take independent tunes, well, presumably the same tune in different variations, and get the ones that are most similar grouped together. We've made a lot of progress and we've fixed a few things, so I'm happy about that. I think we can improve it though, so we're going to look at that today. All right, let me just run tests. I think everything's green. We have a bunch of printouts still. It took a fair bit of debugging yesterday to dig around and understand things. So what we did yesterday, we started at ParsonsCode at the very bottom, up through proximity matrix and cluster and dendrogram view, all trying to understand and make it so that, well, trying to get the best match pushed towards the top. All right, so let's take a look. And we did a fair bit of that. It's not perfect yet. I think we have some ideas, but we'll get there. All right. So the cluster, we got rid of the flipping where it was flipping things vertically to get them in place. The reason for that was whenever it was comparing two nodes, yeah, we were going to do something with average. You compare two nodes, we always set it up so that the lower one would come first. Well, the lower one is almost, elements are always lower than any other clusters. So the elements, the sort of loose elements were coming up to the top and not the most tightly coupled stuff that we liked. So I think if I'm looking right, this node 43 represents the first node. Yeah, so the ones that are zeros, they're these ones tied up against it there. This node here is the best cluster, all right? And you can see there's nothing further left than that. But what I don't like is that it's not at the top. And I think the reason for that is if you form a cluster, we give you credit for the depth. Okay, so let's compare this one, I guess. So 43 versus 44. 43 is the best. It's the shortest, non-zero. Then 44, and then 45. Okay, but if I look at the actual clustering, it's really busy in this little zone because these are all these no scalons, all but two up somewhere else, but most of them, they go together very strongly. And if you just take the depth, you're sort of ignoring how many people are involved in that cluster. So this cluster here, well, it's only, I guess it's slightly better than this one, okay? But I actually like this one better. I'd rather see it up top because it's got 4 nodes in it. Okay, so what I'd like to do is change our distance calculation so when it's deciding which node goes on top, it puts the one where the average is lower. And I think the average I'm going to use is how many entries do you include? Okay, so this one includes 4. I would like to divide its length. I've got to make sure it comes out right, though. Oh, how can we do this? I don't want 33 coming up because I guess it's given a choice. I don't know if I'm making this arrangement, kind of deciding which one to shove up top. All right, so I think what we'll do is we'll take the level, which is the distance, kind of this line's distance to the previous node. Well, yeah. Well, actually, distance from the edge of the text. All right, some of them are clusters of clusters and stuff like that. But the distance, I'm going to divide it by the number of nodes included, and then I'll decide which one goes up top. Yeah, this only applies cluster to cluster. If it's cluster to element, I want the element on the bottom. If it's element to element, it doesn't really matter. So we broke out code to consider those 4 cases of cluster versus element. And we have a case that's the cluster case that doesn't do any special decision making that way. It just says, okay, I'll take whatever you gave me. All right. So I think what we'll need to do is, well, I think we want to give each connector a count and say, how many nodes do you include? And the number is going to be the sum of the 2 children. Okay. So let's see, where's 48? Yeah, so this connects this and this cluster. And I would like to say the count is the count for this one, which is 4, and this one, which is 3. So this one would have a count of 7. All right, so we do have the element list. We can, I know we go about getting it a little slowly, but that would be a quick way to do it. Yeah, let's do that. All right. And I don't know, maybe I can even do it in the code as elements.count. I don't know. Maybe it'd be better in the object. Okay, so let's get to some coding. All right, so we were in proximity matrix. We added this method that actually builds a cluster. So element, and cluster element, well, it's got an element last, so that's fine as is, cluster 1, cluster 2. If the element is first, we really want the element second, so we swap the order here, and then this case is the one we're going to focus on now. All right, so let's get a test. Well, one thing I sure learned yesterday, it's no fun writing these examples. Puts the smaller cluster with smaller distance first. Okay, I don't think these tests actually demonstrate that. It's not smaller. It's really, it puts the cluster with the lower sequence number. Make cluster puts cluster with the lower sequence number first when both are clusters. That's the way we are now. This is kind of the test. Let's call it smaller average distance. Let's make this test work. Oh my goodness. Okay, so I think the situation since diamonds are included. It includes itself, yes. Elements is just the leaf nodes. So I guess it doesn't include itself. It's not counting the interior nodes, it's only counting the leaves. Actually, we have a leaves method too that counts the leaves. So let's see. So an example with average distance. So the situation I think we want, let's make some data. Okay, so if I have 1 and 2, right, they're nice and close. They're going to cluster first. And then if I have 50 and 60, they're going to cluster second so far because 10 apart. Okay, now this is only cluster versus cluster, so I'm going to need at least 2 clusters. All right, so what I want is I want a cluster that seems closer. How's this going to work? Maybe the first element's closer, but the second element is further away. So let's take how about 10, 25? Okay, so 1 and 2 will cluster together. 10 and 25 will, 50 and 60 will cluster together. 10 and 25 will cluster together. They're 15 apart. Well, now I got to make sure these stay nice and far apart. Let's make it 110, 125, 250, 260. Okay, so 1, 2, 250, 260 is 10 apart. 110, 125 is 15 apart. 110 is closer to 2 than 125 is to 250. So 1, 2, 110 will cluster. All right, 250, 260. And they will cluster with a distance of 15. So the current way, the cluster with 10 will look closer. So I think 1 and 2 will be the best. These two will be the next best. And then these two will be the next best. All 4 of those will cluster. And then which one's on top? Is it 250, 260, or is it this cluster? And the way we are now, I think 250, 260 will be on top. No. Yeah, 250, 260 will be on top because their number is going to be lower. Okay. So I think right now they will come out in the order 1, 2, 250, 260, 110, 125. Let's see if that is true, if the way we're doing it now. No. 250, 260 comes out first. How is that possible? Well, this is my way of not looking at the cluster, so I'm paying. Did we give cluster a debug string? No. Maybe that's what I want for this testing. I want to know that 1 and 2 should form a cluster. Oh, no, I think this is reflecting. No. I'm kind of puzzled. So 1 and 2 should cluster together first because they're the smallest distance, and that should be a lower cluster number than 250 and 260. Okay. I'm going to give cluster a print. Okay, so let's extend it. Okay. All right, so cluster has 2 cases, element and cluster. All right, so if I just write cluster, well, let's see what happens. Okay. Yeah, it does. Maybe, yeah. So that's, yeah, that's a good point. Okay, so is that reflecting it? Yeah, okay, I think you're right. So this one may have the lowest sequence. This is sequence number 1, 2, 3, 4, 5, 6. This is 7, and this is 8. But this thing will merge 7 and 9 to 10. And so you're right, this is only 8. And so the way it is now, it shows up first. Okay, and I think what we want, I expect 110, 125, 250, 260. I expect this to be the way it goes. Okay, because I want, these guys have a distance of 15. Is that going to work? Yeah, so the 9, cluster 9 over here, or 10 with all these, whatever that is, should it precede or follow 250? Well, if you go by number, sequence number, it precedes, 250 precedes it. If you go by average distance, I think the average distance is going to be, well, I think the absolute distance is 15 and 1. Yeah, so 15/4 is definitely less than 10 seconds. All right, so this first one should pass because it's what we currently do, and then the second one should fail because it's what we want. Okay, so now let's work towards what we want. All right. Now, I think one case may be enough to drive it because well, it's certainly enough to drive the swap here. Okay, so I want to say if the cluster 1's distance versus cluster 2's distance. Okay, so if cluster 1 distance divided by cluster 1 dot, I think leaves is easier to get, dot count is less than or equal to the opposite. Then we're going to return. Otherwise, we're going to return cluster. Otherwise, we swap. Okay, so we were returning this. Is it not the right level? The ints doubles. Ugh. We'll move this somewhere better in a moment. All right. So it's in the case we're saying this is going to not be true. Oh, got to put the word in. Double. All right. So it will swap. So we expect this code to execute now. All right. Now, it may break some of the orders on some of these other ones because we didn't consider this possibility before. I don't think it'll be very many if it does. Well. Oh, did I get it? Thank you. Oh, that's the warning. Okay. Less than or equal to the level. Plus 2. Okay. Well, I guess I'm glad it failed then. That's pretty egregious error. No, I'm not as glad. All right, 250, 260. Now, do I have these in the right? I want the one with the smaller average. All right, let's just peek in while this is running and see what's going on. Okay, so let's print cluster1.level. Okay, this is 1 and 2 versus 110, 125. All right, so 110, 1, 2 should be first, so we expect to get 86. Okay, and then we'll continue, and now cluster 1 level is 10. That's 250, 260. 2 level should be 15, I think, or is that the 110, 108? Well, that's definitely not right. Okay, I think I need better data. So I don't want this gap to be as big. I still want it 10 apart. Okay, so this, I think if I go 20, let's say 22 and plus 15 is 37. Okay, so these are 20 apart. These are 15 apart. This is 10 apart. All right, let's see if we can do the equivalent. So I messed up the intergroup distances because the cluster distance then is 2 versus the old 110 was just way too much, okay, compared to the 10 difference here. But if these are 20, if the distance here is 20 versus 10, then I'm doing 20 divided by 4 is 5 versus 10 divided by 2 is 5. Let's make this 20. And 30, whoops. 35. Okay. So cluster 1, cluster 2, cluster 3, then 1 and 2 compare with a distance of 18, which is worse than 10. So if you just went by distance, this one goes on top. Now we want it to be 18 divided by 4 is 4.5 versus 10 divided by 2 is 0.5. Okay. And the order should be 20, 35 to 60. Okay. Well, let's maybe, if this works, I'm not as convinced I need the debug extension. All right. And this, let's see how it does. Excuse me. Good. All right. Now, I'd kind of like to make sure both lines get executed in our test data, and I'm pretty sure they will. Actually, even in that one case, it will. All right. So, yeah, our case demonstrated both paths. Okay, so I'm okay there. Let's make sure everything's green. All right, let's rate our tests. Excuse me, sorry. All right, so we made distance, well, made cluster comparison work by average depth. Okay. Average depth first. All right, now let's see it running. Then we'll do some cleanup. We are definitely in need. Okay, no scaling. It's got the 39. Let's cluster it. Okay, and these nodes are, the numbers are the node numbers for this thing. Okay, well, it's more generally, okay, which one was, I guess that was these, right? 39 to 45. Okay, so this cluster is better there. I'm just puzzled that this one is so good. Right, but, well, you know what it's done? It's pushed these zero distance ones up. I don't think we have any at the bottom now. Okay. No scaling, no scaling, no scaling, no scaling. I mean, all the no scalings are pretty close there. This one's a no scaling. Not as close. But still in the same general area. This one puzzles me. He's got 2. He's 75, so he's the second most. Well, I guess by the time his children come in, he's got 80 gazillion children. Yeah, I think it's better. I mean, the stuff I want up top is more up top. I feel like there's maybe a little less line crossing going on than before. It definitely is clearer. Yeah, I'm puzzled why it's showing up here. How can that be right even, huh? And this cluster has, well, okay, its average is 0. That's pretty good, right? Yeah, let's see, 28 and 29. Oh, we can probably tell in down here. Well, okay, those are pretty darn good. I will give you that. They're identical. It's clearly not the same as these two. I mean, honestly, I would say this is almost, oh wait, where's 2029? Well, they almost to me look more like it's kind of covering this stretch than the front. Well, no, it's got that little dip in the front. Maybe not. Oh, I didn't quantize. Let me do that. It's gonna have to make it recalculate. But normally for this stuff you would quantize. Okay. I think the reason it's coming up is it's got it covers 2, and then this one covers, like when we're calculating 75, we're comparing 0, this one's level divided by its number of nodes is 2 is 0. And then this one, all the other nodes except 1, dividing by whatever length this is, well, it's still going to be bigger than 0. And so this one looks a little shorter. Now well, length matters to the similarity calculation. So if you took 28 versus 22, it's about half as long, so its best score is only going to be a half. Okay, so it gets kind of we sort of just, I think we're basically treating every other note after the first, every missing note as a repeat. And, in R or D or U, we're just saying let's assume it's the same note and just carried through and let those be different by that distance. It might be we're saying it's just wrong and doubling it, but I think we're just treating it as one. But at any rate, these two, in some sense, are more similar than either of those and this one or this one, because this is just so much longer. Doesn't quite make sense. Um, now we could make, well, I'm not sure what the right way to go is. The similarity between these two is, which one? So where is it? Oh, it's 28-29, right? They're still pretty close. Um, we could just say I don't know, like their distance is 0, but it's a very short 0. um, hmm. So I don't know the right solution because, like these, all of a sudden you've got this one that's way long. Okay, I mean these two look pretty similar to me. Maybe not perfectly, but more similar than this one does. Now, the order here, I think it should probably reflect the same order as here, but this, I don't know, this thing of the short ones getting credit for being such a good match. And if you trimmed everybody off to the shortest one, they wouldn't look so good. But you'd also lose a lot of information. So I don't know the right solution out of here. So I think my conclusion is, given the way we're doing things, I think it's doing the right thing. It's putting the 0 over the 0.0005 as far as which one comes first. It's a little off. I mean, really, this would look better if this were down lower and, down here by air seventh. Let me do a little trick. Let's delete 29 and see what happens. Where's our data? NG2, no scan. Okay, let's take no scan. We'll copy it. NG2 is kind of a scrap one. Okay, we'll find 29. So I delete that similar one. And now we only have 28. My expectation is that drops to the bottom. All right, and the whole thing looks better. Yeah, I agree. Yeah, okay. In a way, it has to because it's an element, and elements always come after the big blocks. It wasn't a cluster anymore. But a cluster of 0, I don't know. That's a bit misleading. I'm trying to think about it from the music end of things, right? So I've collected 2 songs that are literally note for note identical. I guess that's interesting. But boy, that distance doesn't seem fair to treat them as different nodes. I think we would say, like, this node looks like the furthest left. I should look at its number, right? 41. Okay, 38, 39, 40. Okay, yeah, so this is the best match. And if you dropped the other node, it would still be the best match. These two, Yeah, interesting. These two get pushed up. They look like the best overall match because the 0 plus this one divided by 3, the total distance there. This one is a little bigger. They have different names. Yeah, they do. Well, this one is, one accent difference. But it's always the names it's very hit and miss. I mean, gosh, I had a jam I was in last night with Don Petty's kind of a dulcimer legend as far as old time tunes, and we played a tune. He's like, well, so and so calls it this, and so calls it that, and this person calls it this, but it's basically the same tune, and that's just super common. You see the same thing when you look at some of the old tune indexes and stuff like that. Boy. I don't know if we can penalize this 0. I mean, the unique count is interesting. Yeah, they should and they shouldn't. Unfortunately, well, for whatever reason, the Parsons code. Remember, it's kind of like a derivative. It's sort of giving the slope up or down of the notes. But even though these two look, well, find two that look identical. It was 28 and 29. Oh, I deleted the one that did. Okay, let's find two other close ones. Well, these two will do. Okay, 1 and 39, maybe they're identical. They have the same Parsons code, but this one might be jumping down an octave, and this one might be jumping down one note. So the music is different, or music can be different. This Parsons code doesn't differentiate it enough, but it's sort of directionally useful. And if both tunes are going down with the first 2 or 3 notes, and then up a couple notes, and then down one and up a couple more, that sort of pattern indicates some similarity regardless. So it's not, they're not identical. There's no guarantee they're identical, I guess, put it that way. I mean, they're probably very similar, but not quite the same. But you don't know. You can't tell. But as far as calculating, I don't know. I'd love a way to throw away these two and count them as one. As far as clustering goes, I would still want to show them both, but I don't want to divide by, like, 43 is dividing by 3. I think it's got 3 nodes in it. Yeah. And these two are identical. So it doesn't seem fair to weight them the same as 3 other independent tunes that actually come out very similar. But on the other hand, I'm very happy with this. I mean, most of the stuff on the top is close and most of the stuff on the bottom is far away. That strikes me as a good thing and not something to get rid of lightly. Okay. I don't think we have the perfect metric, that distance metric, but I think it's good enough that the patterns of these things or the clusters of these things will show up. Some of these are such subtle differences. That's a pretty thin gap. Both these are pretty thin gaps. Okay, but I'm going to call this done for now. I think, a true, what do we call it, agglomerative clustering specialist would probably be able to give me a better formula to use or better advice. I mean, I think we could kind of wing it and say if they're identical or under some cutoff, then don't count them as separate nodes when you're dividing, would probably help move up. Well, it might move this one up a little, because then this would not be this. Well, yeah. I think it might help, but I don't know how much. But anyway, I think I'm ready to call this one done. We got plenty of other stuff to do that involves cleanup and that. So I think we've done that, and I'm much happier with the result compared to where we started, especially with all that flipping and all that. But they were kind of showing close nodes, not necessarily too close together, and I think we have them much closer now. Okay, so this is sort by level divided by depth. Okay. It's not depth though, it's okay. Let's see. Remove print, spread out horizontally. Yeah, that'd be good. Initial selection, stage node selection, selected nodes path through the filter. That's really a point of this. I don't know how we're gonna. That could be a ton of work. I don't know. Let's see. ClusterStage use green foreground. Yeah, that's okay. Speed it up. That might be interesting. I think. Well, I haven't used the profiler very much. I don't think at all in this project. Maybe one or two other minor things. All right. Remove the print. So let's clean up. In our nodes, I don't need the first number is the node number. I don't need them in here either. I don't think. I'm going to trust that the clustering is correct. Okay, so let's find those. They're in dendrogram view. That is leaf.sequence number. Okay, and our diamond. Okay, we extracted a method here. Now let's. Okay, I haven't changed too much, but being paranoid maybe. All right, and let's just find print. I think we have one in here. Yep. Okay, so when we don't see it in here. There's something printing in here I saw go by. Yeah, proximity matrix. Okay, but during the drawing we printed stuff. Okay, so you may have seen it flipping by in the background. All right. And that we got rid of. Okay, let's look for other prints. The proximity matrix and new cluster connection. Okay. Right. Tests. All right. Didn't see any, but I didn't read fast. Okay, no print stuff coming out that I saw. All right, remove prints. And we'll check that in. Well, let's see this one. I don't know, this problem may be painful. What we would like, well, here's a prime example, 45 and 46. You can see the space around the diamond here is overlapping the corner of this bracket. We also see we're drawing in our node. We did earlier some work to kind of rearrange the drawing order to make so the higher number nodes got drawn first, so lower number nodes would draw over this line, but it might be nicer to just not draw the line there in the first place. And actually, I would love to shift these over so that the gap here, I would like it to be certainly at least half a diamond and maybe a whole diamond, because like this situation, like we don't want these two overlapping any. So I think what I would ideally like is the line for a cluster to start drawing at least, well, certainly drawing half a node away, half a diamond away. But I would kind of like to put a minimum distance on each line, or, well, it's going to be hard to figure out, unfortunately. If each line drew, well, I kind of want to think about it coming over here. If I put half a diamond's distance, would that help? Well, I think half a diamond would help here and here. And to some extent, I think it would help here. How did we set the size of those diamonds? Position, system size, font size. Yeah, I'm not sure either, because the two brackets, like, I mean, what if I drew, well, certainly I can shift them over half a space if I can figure out what that space is. If I shift them over half a space, I got to do that to both sides. No, I got to do it to this. I only want to do it on the cluster sides if it's drawing over a cluster, which definitely sounds like it's complicating things. So any line that's drawing through a diamond, I don't know. Well, one thing might be like, what if this got half a diamond's worth of drawing, even so, like if everybody has half a diamond worth, this would get little short stubby branch legs and make a tiny bracket, which I think would be a better look. So shifting, what am I doing? Well, I guess what I'm doing is I'm kind of putting a protective barrier here if this bracket is half a diamond long. And then same thing here for the start. But the real thing I want is I want these. Well, I almost wonder if I'd be better off going into pixels, but I mean, we sort of can tell, right? We can figure out, we know font size. That's a constant. So 24 pixels, theoretically, it's going to be half, I think, because it's symmetric, both directions. What if I drew each line 12 pixels longer? What's that going to mess up? let's I'm tempted to just experiment a little and see what we get. We got our draws like this, connector.top. Okay, horizontal line. Well, I'm really going to just kind of hack it out. I'm going to say draw everything 12 pixels longer horizontally, and then your starting point should then be 12 pixels to the right. Okay, only the X things. All right, now I think this is going to screw up when they have children of different heights. We'll just do the small file for now. Yeah, okay. Well, the y-axis is right. Why is that so? What is this line working in? Oh, it's line that's scaling. Yeah, this is kind of where I wish I were in pixels up here. Well, we'll try dividing it and putting it back. Okay. Yeah, there's more cleanup we should do, really. You're right. We'll put this. Okay. That's kind of interesting. And the 12 pixels looks kind of about pretty close to right. Okay, let me run on the big set and then we'll go back, and I know at least one thing I was worried about. Yeah. Get to wait twice. Okay. Yeah, so that does give us the effect of brackets there. That I do like. If the diamond were scooted over, I think it would be very nice. I'm not seeing, how wrong am I cumulatively? That seems to be a little bit over the edge of the diamond, as does that. So I don't think I'm picking up all kinds of space. But somehow it seems like this guy that it's including 18, 20 other nodes should somehow have to adjust one side more than the other. Okay, tell you what, let's revert this. I think it was a good experiment, but I'm going to be strict to myself and revert those changes. And let's go back, proximity matrix. Actually, let's make sure these tests have no comments either. Okay. Oh, format. Oh, there's my print, basically. Yeah. Okay. I don't see any comments. All right. Priority matrix. Okay, the thing I do know, this one, right, this should be a method. Well, maybe even just this would be good enough. This is sort of average level, maybe. Let's extract a method. Average level of cluster 1 is same as average level cluster 2. Okay. All right, and now, well, I want to do a move method. Unfortunately, we don't have that in Swift or Xcode, but everything in here is about clusters, so we should be able to move, provide this method on cluster. I guess I'll just copy and paste wherever cluster got to. Okay, and I will delegate go back. Let's return cluster 1.average level. And we'll make that a variable. Variable of double, and that's self.level over self.leaves.count. Okay. All right, and then we'll flip this to call cluster 1.average level. And then no one's using this. Okay. I probably should maybe do the performance tuning now. I'm going to take the method and just walk it through. Can I double click this? No. Okay. This is our cluster algorithm. Okay, if it's empty, do that. Find out the next sequence number. While there's still more clusters to build, find the best two, the two that go together the best. Find their distance. Make a cluster with that distance. Remove the old two, add the new one. Repeat until you're down to 1, and then return it. Okay, that's all right. I don't mind the comment there. This is what we just did yesterday and today. Forming the cluster, we want to rearrange it so it looks the best with more relevant more closely coupled stuff up top. Okay, so if there's an element, that we always make sure that's last. If it's two clusters, we check the distance. I don't think that would be improved by. Yeah, I don't think turning it into one statement would improve it really. I guess I would store the variable and then swap. I would swap, otherwise not. Yeah, okay. Best pair, okay. The funny thing is we return the best pair, but we don't return the distance. So we are recalculating that down here. I believe that's going to be the same two things involved. Okay, distance from sequence number to sequence number. All right, so we know the least distance, but we don't do anything with it. So that's one thing that bugs me. Performance-wise, it means we're redoing a distance calculation in extra time. Probably doesn't affect the order of magnitude, but it does slow it down. And then also we're generating all combinations and then filtering out. So again, I think you could rewrite this as a loop, a pair of nested loops, and do better. Maybe not. This list of sequence numbers changes a bunch. Maybe not. Well, we can go through the matrix. Yeah, we could go through indexes on the matrix or something like that. Okay. Distance. So we find these things. Now this is we're maintaining things in a list, and maybe this could be hashable. I'm kind of guessing at performance things, but at any rate, we find the two clusters. We figure out their lists of elements, and then we take every element with every other element, and we map them to their distance and take the minimum distance. So whichever two, if you have two sets of numbers, whichever number in your set is closest to the other same one in the other set. Now in arithmetic, integer arithmetic, that's pretty easy to figure out. You could take the min of one group and the max, but we need to go by distances. And so we're comparing every pair of distances in those two sets. I don't think there's any guarantee. Yeah, I don't think we can use any structure of things to know that we could get by with less. Okay. This find, yeah, that one kind of bugs me a little, but okay. And count is reasonable. All right, so I don't think it's the best ever, but I think we've got some performance things we could do, but I mean, clarity-wise, it's fair. And let's take a look at dendrogram view. Now, how do you draw a line? How do you draw a vertical line? Y scale, Y scale, Y scale. I mean, it seems like I could do the Y scale in there. Branch.y. What's Y scale? That's a font size. Y scale's a double. Branch.y you think would be a double. So I don't think I need this double. same argument. Don't need that one. All right. Let's run. Sequence number to cluster. Yeah. I mean, the example in Wikipedia, right? They use a big matrix of which it's symmetric, so everything past the diagonal is kind of boring because it's the same as the other diagonal. So I don't know. We're maintaining it as a list. Now, it's not horrible. I mean, I think the 40 we have is probably more than most songs have. You might find one with 200, but you're not going to find one with 10,000. Okay. Unless you're just throwing everything in a bucket and trying to see if anything pops out. But, so a linear search of 100 items, it's not all that bad. You're just looking for a numeric field in there versus hashing where you'd have to calculate the hash function and then test equality anyway. So, all right. I guess I got to run it. We just took doubles off. I don't think it's going to cause any real issue. Okay, they're looking okay. All right. But I do think we're doing X scale calculations in here. I think we could do Y calculations as doubles scaled as well. Okay, so we'd be putting it online to know the scale and use that. All right, so I'm going to say, well, that's not quite what I intended. Let Y equals Y scale times Y, and let delta Y equals Y scale times delta Y. Okay, and then I'm going to take this off the two Y values. And I don't know if this might be just as readable at this point. I can stand that. I don't know if the delta thing is paying off. Well, I'm definitely liking that better. All right, what would happen if I took the delta off? I would be telling you, hey, you provide me the second number. Okay, so here that would be branch dot y. This would be branch dot x plus length dot x. I guess it's okay. All right. Let's reload. Rerun. Okay, looks the same. Okay. Now, would I be happier multiplying it in line? Let's try that. Take out these 4 lines. Still looks good. All right. I think that's better. It's a pity this... Is that... Where's inner frame width? Yeah, we can move this up. I don't know if that's still legal. No? Good. Okay. Now, one thing we talked about was maybe making our connector time. Yeah, good idea. Making our connection know the leafs and draw it directly from there. I haven't pursued that any. Okay, we still have some Y-scale adjustments out here, but I think that's okay. All right, we'll kick off one more run. Again, should be no changes. Oops. And the cluster. All right. All right. Yeah. So let's take a break, 3 or 4 minutes, and we'll come back. I think we're due to. We'll start trying to figure out the performance thing. Let's move this up. It can only help us, right? Because we're doing this over and over with these graphical view things. All right. So 3 or 4 minutes, and we'll pick up from there. Thanks. All right. Welcome back. We'll turn this on again. All right. Speed it up. Okay. So this is instruments, and I know I've brought it up for a few occasions, but I don't know, not much. Is it? Well, let's do that. I think it runs, and then we do something, and then it judges. Build slowly, and then we run it. I don't know. Do I run it now? All right, I think I messed that up. It's built for profiling. Profile without building. How do I get it to run? Okay. Thank you. Okay. Turn on cluster and hopefully things look. Well, they ran so fast. Okay. Stop. I should be able to zoom in. Well, I can't really believe Swift UI is the thing taken up all the time. I wonder if there's. Usually there's a way to get a linear view of this as well. Is that going to do it? I don't think that's telling me much. Most everything happened in the main thread. Yeah, I don't know. I think there's, well, okay. Yeah, I could redo that, I think. Let's, is there clear? Well, no, I didn't want to do that. Okay. I can at least start calculating. I mean, I can start the recording when I've already loaded it and I just click cluster. So product, build for profiling. We did that. Profile without building. Okay, so now start recording. Well, I'll give myself a pause. Okay, so now that's that one. Here's cluster. Seems so much faster. Wow. Okay, let's turn this off. Volume is too high for recording mode immediately. Some did had to be moved forward. All right, cluster again. Is he still running? That's so fast, I wouldn't worry about it twice, but I don't know what's going on. It's funny that the mouse pad is vibrating at me when I cross over these zones. Try saying recording mode to deferred. Well, I assume it is. I don't really know though. Instruments. Okay. Where do I set recording mode? Sure. Okay. Wow, no blips at all with that. Lots of deferred stuff. But that was like a second, right? I mean, stop. So weird. Let's build for running. One, 1002, 1003, 1004, 1005. It seems so much faster with the profiler running. let's see. Yeah. Yeah. I mean, usually I'm willing to take that hit, but for real profiling, we don't want it. But I assume building for profiling does that. I don't fully know. Okay, but okay, build for profiling. Okay. Profile without billing. Why don't I have profile? That was no 5 seconds. How crazy. Usually it's slower when it's there. Okay, I can see things now. All right. So that looks, I think, well, I told it to build without debug mode, and I did that. Maybe, let's see, is that project level? I don't know where I'm. Well, I don't know, but now I can see stuff in here. Okay, hang. So I think that hang is our calculations. Okay. I bet that's probably the drawing, and this is the calculation of it. Now, filter. I don't know. Cluster. I would hide system calls and stack trace. That seems like a good thing. Heavy stack trace. Collection map. ParsonsCode analyze. Interesting. Because we can definitely speed up ParsonsCode. This certainly happens a lot because there's just so many notes. Turn it off in a schema. Yeah. Not quite sure where to turn it off there, but I think we're getting enough visible data here that I can run with it. All these one level deep ones, they are not giving me information. Yeah. Like, I'd really like to just only see my functions. I think I'm getting every little twiddly function. But I get her pipeline process. Okay, yay, that's one of mine. That's progress. Okay, now we're getting into these. All right. Best pair is a candidate. Distance from 2 looks like it's pretty minimal. Okay, these all three. So 29, 49, 52, 62, 65. Most of this is tune.distance. Okay, now we probably call it a lot because we're comparing everything to everything over and over. So yeah, we're going to call tune.distance. All right. Oh, samples. There's distance. Okay, within here, allocating init. ParsonsCode init. Okay. ParsonsCode analyze. All right. So one thing we can do, and I think is reasonable. All right. So let's find ParsonsCode. Okay. So a ParsonsCode comes in. You give it a list of symbols, and it runs through every symbol. Basically, it gets all the pitches and runs through them all and calculates that up, repeat, or down thing. It does this every time it takes a tune. So I think what we can do is we could, this is static information. So given a given tune, its ParsonsCode never changes. So there's no reason to calculate it over and over. We can make the tune hold it. There's a cost to doing that, but we have 39 tunes coming in, right? And we're calculating ParsonsCode every time, every pair of clusters, and then within a cluster to compare two clusters, we recalculate all their ParsonsCodes again. Okay, so I know it's expensive. We could also, another way would be to make sure our tunes are identifiable, and then build up a hash code structure that holds all their ParsonsCodes. I don't think it's terrible that the tune knows it. It is kind of a static characteristic once you know the notes. Now, the quantized one. Right, let's see tune. Open tune. Yeah, it costs memory. Memory's cheap. It's a pointer to a string. This string space I don't really care about. Yeah. All right. So when you build a tune, you give it parts. holds a measure map. Okay, then you can redo it. So the two ways to build a tune, right? Okay, so let's find Parsons code again. I think I'm gonna pull this one left. Let's see. Okay, let me go back to instruments. Let's see if we can characterize what we're looking at here. In the 2%. Oh, there we go. Okay, so Parsons code, static tune distance. Okay, let's go look at that thing. All right, calculate the Parsons code of the two things. Okay, distance is called a lot. Now, I don't know how I get the samples. Can I? I really just want my user methods. Process. Oh. Well, let's look for tune. Tune.distance. Other frames. Gosh, I would really love to get the numbers over here. There's usually a couple ways to profile. One is you sort of, well, you can instrument stuff, you can snapshot, and then you can count stuff. But I would really love to see in here like coverage or counts or something. All right. But we definitely feel like tune.distance is the culprit, at least the main one. Where's okay, so 70% of our time is in ClusterStage transform. That's also suspicious to me. Let's go look at that. Oh, ClusterStage.transform. Okay, it's just doing the work. Yeah, it may be the distance calculation is expensive. Okay, but if we see each of these, I mean the 70%, that's 65%. So most of it is in there. There's a little bit of time destroying symbols. Okay. Not sure what that means. But at any rate, a lot of time spent calculating tune.distance. Within there, okay, here's 29%. 21% is spent allocating and of Parsons code. So that's definitely the Parsons code setup. He does tune.symbols. I really would love to know. I mean, yeah, like I could go study and find out. It might be a good plan. All right. He's doing this. I mean, most of his stuff is not that heavy, but the allocation and tune.symbols seems to be a lot of it. And we know tune.symbols is called over and over and over because we call that over and over. So I think I'm justified doing this. Let me close tabs. Let's open Parsons code. Okay. So I think this gives us back the Parsons code, right? So it's returning this whole thing. Okay. So who calls this? Well, it's going to be our Parsons stage probably. Oh, init. Parsons Code report. Okay, so for each tune, we get Parsons Code with its notes. All right, so tune.symbols. Okay, can we tell? Well, I guess we could say Tune has Parsons Code is one of the things it will tell us. And I don't want to make it the class. Well, I'll leave it there for now. Okay. Let's just start off wrong, and we'll open Tune tests. Tune distance using Parsons distance. Okay, that's reasonable enough, right? So let's test Tune knows its Parsons code. We'll parse a tune. We'll check that tune.ParsonsCode is equal to, well, star, G is higher, A is higher than that, I think. All right. Okay, so this will fail. A little more than I thought it would. This is private set, public get. Okay. Sure. Okay, I think it'll come back star. I don't know if I'm... Okay. Yep. Star is not equal. All right. So the way to calculate a Parsons code is called Parsons code with the notes. Okay. So let's set it here. Equals Parsons code with symbols. I don't know if I have to say notes symbols there. Okay, if you rebuild it or you modify it, then we do it after. Oh. There's... I guess it's dot description. Okay. All right. So now Tune knows its Parsons code. All right. So anybody who calls Parsons code directly certainly in production code, is suspicious. So Parsons 1 is really tune1.ParsonsCode. Oh, man. That's the description. Maybe I should give it the Parsons code. Okay, we're just going to hold Parsons code. Let's do defer. Really? For store properties are initialized. I don't know if I can just. So that's not necessary now. Okay, so he knows that. All right. Okay. Parsons code dot description. Okay. Okay, now we want to find who's calling this. Can they do it from a tune? Okay, so I think coder.description is really tune.ParsonsCode.description. These two. No. Coder as pairs. Okay, this is the production code. Okay, so we got Parsons code. Well, coder is really tune.ParsonsCode. We'll work on the name. Okay. Now, coder.description, coder.as pairs, and who's looking at notes? Okay, so the final report, we're not rebuilding a Parsons code. We're just using the one on the tune. All right. And who else? This is Parsons code net. We want. Okay. That one we did. Tune. Yes. Okay. Tuned. Okay, so this should be tune1 dot Parsons code. Tune2 dot Parsons code. And distance from that to that. Tune1. And I'm pretty happy inlining that. Okay, again, that should be clean. Good. All right, now those tests. Everything was in Parsons code tests. Okay, so those may be okay. Yeah, I mean, we're constructing Parsons code and asking questions about them. I'm good with that. We don't need to involve tune. This is direct tests of Parsons code. Okay. Everything should be good. Okay, so update test to use tune.Parsons code where appropriate. All right. Now let's try and repeat that process. I think I lost my. No, I still have that. Okay. Um, 6.77. So kind of a 3-second. I don't know if it'll tell us filter duration. 6.54 to 8.05. So 2.5 seconds. All right, let's duplicate. I don't know. I don't know where it's putting it or what it's doing with it. Run. Okay. So I can make another run. Okay, so let's make sure we're built for debugging, profiling. Start a recording. Okay, we'll open our file. Give a bit of a pause. Cluster. Oh, that's much faster. Okay, and stop. Okay, 12.8, 13.8. I mean, it cut a second and a half off. That felt fast. I don't know why it's running so fast in the profiler. Let's just do a run. Yeah, that's instant enough. Okay. I thought we'd have to do a lot more than that, but all right. So I don't think we've made any changes. All right. Speed it up. And what we did was make tune calculate Parsons code just once, rather than for every distance calculation. Okay. Let's save that. To do. Okay. I'll go back to this, I think. Better to have an explicit empty cluster. I don't think we'd know that. Selection, initial selection. You know, I might fix that first. Yeah, I could ship it like this. Maybe a little work, but I could ship it like this, whereas selection I really do think matters. So let's see. That's in, well, let's close. Get back to dendrogram view. We're going to spend some time there. All right, so here this selection. Right, where's the connectors? Connectors gets built when we draw. Connectors is not held. Does the cluster knows? Oh. Let's see, cluster. He knows the sequence number. Okay. All right, so I think I can do it from the cluster. Okay, so I do self dot selected elements. Well, I guess, yes, if cluster is not null. Okay, self dot selected intervals is set of int of, well, cluster.leaves.count. That's the sequence number of the node I need to find. Can I find it from the cluster? I guess I could ask for leaves. Okay, so the best match we have is the first one after all the leaves. Okay, so well, this is all the leaves, so this is really leaves.count. Okay, since leaves is from cluster, yes, that's the same thing. All right, that's the best match. And then we're going to put in here best match. Match. And then, oh, I got to find the actual cluster though. A leaf is a cluster. Okay, best match equals leaves dot first where $0 dot sequence number equals leaves dot count. Okay, so we're we got best match is a cluster. Okay, and so its children dot I want its elements, I guess. Okay, we know he's a bottommost cluster, so he's got two leaves underneath him. They're going to be the elements, and those are the ones we want to select. Any elements I need dot sequence number. Is that not right? Okay. No. Elements. I guess I want leaves. No, huh? Leaves has 39 elements. Yes. Well, the leaves do not equal leaves.count. Yeah. Because leaves.count is going to be bigger than leaves, any index in leaves. Okay, golly. I'm trying to get to leaves.count. I'm trying to get to that element of the cluster where leaves.count is it. I don't know if I can do that. Well, I guess I'm asking for a find function. Okay, cluster tests. I think the level, no, because the level of elements is 0, but we could have, like we did, we had two identical elements, so their parent in the cluster had a 0 level as well. So I really am looking for this leaves.count is a good thing because it's, we've assigned all the elements, to the leaves, those numbers, and then the count of them is the first cluster that's being created. And that one is going to contain the two best matching things in the whole calculation. So it's the one I want to select. So that'd be one of our 0 pairs will be selected. In our case, because we have zeros. So I think if we have a find, it's going to return that item. Okay, so let's make element equals cluster.element. Its number is 1 and its contents are 5. And we're going to say CT assert nil. Well, no, I guess let's do both. XCT assert equal element.find 1. So sequence number should return element. And element.find 2 should return nil. Okay, there is no find. All right, so I'm defining that. And this is going to return a cluster of E optional. Okay, switch self. What's cluster got? Level we don't care about, and cluster 2. Okay, whoops, this test should fail. Good, okay. We can easily fix that. Let's call this expected target. If target equals sequence number, return self, else return nil. We'll do that the other way around. Oof. Okay, and now a more complicated case. Okay. Cluster can find itself. Sequence 2, 0.5, we don't really care. Element. Okay. We want to assert that find of 2 returns cluster. Okay. Oops, I just paste chunk. No. What? Nil. Cluster sequence number. If target equals sequence number, returns self. That makes sense to me. How do we do cluster.find? Okay, let's make, okay, we've got element 1. Let's add element 2. 2. 3. Whoops. 2. 3. Okay. Got this 3. Four. 5. 5. Let's do cluster 1 and E2. Okay. If it looks for 1, well, 2 is interesting enough. It should return E2. And we're going to do cluster 2. Okay, so it can find E2. It should be able to find E3. Okay, so we know it checks both children, and I think that's good. All right, and it will fail. Right, okay. Okay, if find of target is not nil, then we're going to return, well, I guess we got to save it. And it's also cluster 1. If cluster 1, well, say return self, just to make, as we haven't tested that last case. Okay. These should now pass. C2.find 3 should be E3. What did he find was TuneSim cluster 4. Returned self. Oh, okay. So that's that last case. I'll still add a kind of confirming test for that last case. Oh, still off. Ooh. Nil. Okay, element 3. Did I build the cluster right? No, I did not. Okay, so it shouldn't be able to find 7. All right. Back here. Okay, let's try this again. Making it easier and easier, I think. Okay, so get the leaves. Best match is a cluster. It should be Cluster.find leaves. This is I don't see why it's got a problem there. Is it looking ahead? Yes. Okay. All right. Now, if we found one, all right, we're going to take its sequence number. We're going to take its first leaf sequence number and that sequence number. And I don't know if I can. Type option. Oh, this is cluster bang. He still doesn't like that. Okay, let's. Okay. Okay, so we've got, this is node 1 and 2. I thought I took those numbers out. I must have reverted something. All right, but I think that's 39. Yeah, so we have numbers 0 through 38. This is 39. It's our best match, and it's a 0 weight, and it's good. I don't know. That's... seems like a lot of work. Oh, it is a lot of work. Okay, this is a cluster, right? If it's there, equals, oh no, it's in connector, isn't it? Okay, maybe I should be calculating connectors sooner because connectors have the list of sequence numbers. Sorry, the set of sequence numbers. Yeah, we really should. That's why I'm not liking this. Yeah, we still can't. I guess when I start, well, I think we left them cleared on initialization. I mean, they start out cleared and then we're adding stuff to them on init, but there's a hole there somewhere. If we read a new one in, I don't think we're getting a new stage. All right, let's see how that goes. They start out cleared and they get set, so I think in that sense we're okay. Cluster them. All right, but I think if we switch, I mean, I can close them and open them. That should be fine. If we switch though, yeah, we got the wrong thing selected. When does that show up? Well, it may be a function. I think we had a to-do for this, right? Stage should own the selected elements. Yeah, something for next week. Yeah, we did run into this at least once, I think yesterday. All right. I think I have it for initial selection. I think if stage owns it, so updating stage updates initial selection. Okay. All right. Yeah, something for next week. So next time is Tuesday, Eastern Time, 2 to 4:30, UTC 6 to 8:30, both PM. Thanks, Mudshark in particular, for joining today, and anybody else that's here. And have a good weekend. I'll catch you Monday, I hope. Bye-bye.